Um, the brain is an energy-demanding organ and relies on efficient ATP production, while glycolysis as well as oxidative phosphorylation. Among wearers of brain cells, neurons and glias inject with each other to form a complex metabolic network, and their metabolic patterns and metabolic elasticities to glucose may be different. Mountain's evidence also suggested that AD shares multiple characteristics of metabolic disease. For instance, the impairment of in cerebral glucose metabolism is considered as a typical feature of AD, and its occurrence precedes cognitive dysfunction for decades in patients. Therefore, the glucose hypometabolism in AD also functions as a player in addition to its role as a biomarker in the pathogenesis. In many different kinds of cells in brain, microglia are brain resident phagocytes, facilitating the uptake and proteolytic clearance of neurotoxic oligomeric forms of Iype and plaques. Activated microglia express several glycolytic enzymes, resulting in enhanced ATP production. Considering that glucose availability in the brain is finite, and the glucose hypometabolism in the AD brain, it has been speculated that microglia possess ability to flexible use of other forms of energy substrates, especially in AD. The recent years, the microglia metabolic reprogramming is very hot. Many research was working on that. Hexokinases are the first K-limiting enzyme in glucose metabolism, converting the glucose to glucose 6-phosphate, catalyzing the first commitment step to glucose metabolism. Among the 4 HK isoforms, HK1, 2, 4, we can see that in HK2 has 2 catalytic activities unit, and only HK1 and HK2 can have the mitochondrial bonding motion. Because it is the first rate limiting enzyme in glucose metabolism, hexokinase HKs draw our attention. We can see that HK1, 2, 3 can express in the brain, including in cortex and hippocampus. First we analysis and found that mRNA expression of HK2, but not HK1 and 3 increased with age in 80 patients. Consistent with the human data. Here's the human data. Consistent with the human data, a significant increase of HK2 was observed in the cortex and hippocampus of FAD mice compared to the wild-type mice. by comparing HK2 expressed in cultured neuron, astrocyte, microglia, we found that HK2 expressed most predominantly in microglia, and Iype administration significantly increased HK2 protein levels in primary microglia, but not in the astrocyte or neurons. In addition, we also detect many genes in the glycolysis pathway, and found some of them also elevated when treated with Iype. Immunostaining using microglia specific Iype1 further revealed that HK2 expressed especially in microglia in the cortex and hippocampus of 80 mice brain. To confirm that this finding, CSF1R inhibitor PLX3397 was used to deplete microglia in FAD mice. After 21 days of a PLX3397 treatment, so we can see that both Iype1 and HK2 positive signals significant both were significant decrease. Consistently, increased the percentage of HK2 positive microglia over the total microglia was observed in both the hippocampus and the cortex of FAD mice in the age dependent manner. Most of the HK2 signals was also found to be located around the A-beta plaques. So together, this in the patient, HK2 staining intensity in plaque in the plaque associated microglia was also significantly increased. Here's the patient control data. We can see that in 80 patients, the HK2 signal also expressed in the microglia and significantly increased in 80 patients. This result indicates that HK2 expressed increased in A-beta plaque associated to microglia. To explore the role for microglia HK2 in AD pathogenesis and progression, we first generated the HK2 flux P mice, and then crossed with CX3CR1 and then in the background of FAD mice to abate the HK2 in microglia, intragastric administration with 20 milligram tamoxifen was performed in mice at age of 5 months for consecutive of 10 days, followed by behavioral and pathological analysis at age at 6 months of age. As expected, the protein levels of HK2 was a significant increase in the FAD mice compared to the control mice, but whereas the HK2 was nearly undetectable in HK2 CSKO mice and Cisco FAD mice, indicating high conditional knockout efficiency of HK2. Iype1 and HK2 double staining further confirmed that microglia HK2 has been knocked down in Cisco FAD mice. We can see that the microglia in the healthy mouse brain typically exhibited ramified morphology, indicating a small soma with fine cellular process. In contrast, in microglia in mice brain showed ameboid morphology, indicating significant decreased cell processes and increased cell body size. Well, the ameboid morphology of the microglia returned to the ramified morphology in cisco FAD mice compared to FAD mice. We analysis the morphology of the plaque-associated microglia and found that there were also significant altered. We also found that the plaque load was significant decrease in most foreign brain regions, including the hippocampus and the cortex, in cisco FAD mice. Moreover, the behavior test showed that HK2 deletion in microglia rescue the memory and cognitive impairments, and the synaptic associated proteins in FAD mice. In addition, HK2 has some inhibitors. HK2 inhibitors lonidamine and 3BP was used to assess the effect of HK2 pharmacology inhibition on AD-related pathology. We can see lonidamine actually is a HK inhibitor, and 3BP is a HK2 inhibitor. We can see after the two inhibitors treatment, so we can see that the plaque load and the memory-related behaviors, memory and cognitive-related behaviors was rescued. And the synaptic LTP was also rescued after the HK inhibitor treatment. In addition to the A-beta clearance, both neuroinflammation factors and the activation of microglia was also alternate by the 3BP administration. So first we tested the migration ability of a microglia, notably genetic depletion or pharmacology inhibition of HK2 significantly promotes the migration ability of a primary microglia or BB2 cells. BB2 cells is mouse microglia cells line. So then the quantitative assessment show a significant increase of overlapping areas of AB1 and A-beta colocalization in lonidamine and 3BP administration. Furthermore, the phagocytosis of A-beta as measured by FAM labeled A-beta 42 uptake was increased in culture primary microglia treated with lonidamine and 3BP. Since Iype itself can elicit the phagocytosis of the microglia, to test whether lonidamine or 3BP can promote the microglia phagocytosis in the absence of Iype, FAM microspheres alone was used to evaluate the phagocytosis. Indeed, the lonidamine and 3BP can stimulate the microglia phagocytosis of FA microspheres independent. On the contrary, HK2 overexpression decrease the EV2 cells phagocytosis. We cultured HK2 microglia derived from the cystic mice. We wondered if the microglia form the phagocytosis or because HK2 is the first step enzyme in glycolysis. We wonder whether the ATP increase or decrease after we inhibit the HK2. To our surprise, we found that the pharmacology inhibition or genetic deletion of HK2 dramatically increase, not decrease, increase the ATP production in microglia, while decrease the ATP production in primary neuron. And astrocyte, regardless of the A-beta treatment status. That means that when we inhibit the HK2 or deletion HK2 in neurons and astrocyte, the ATP will significantly decrease, but in microglia, actually it's not decrease, but increase the ATP production. To further confirm the potential of this finding, we identified the human ESC into mature microglia cells according to the established methods in Beijing Tongren Hospital, and treated them with 3BP. Notably, we can see that the ATP, the 3BP can also increase the ATP production and phagocytosis of in the human microglia cells. Together, this data suggested that HK2 inhibition uniquely triggered the ATP production in microglia, but not neuron and astrocyte, which may contribute to elevated microglia phagocytosis abilities. To gain a deeper insight into how the HK2 inhibition upregulates microglia ATP production and phagocytosis, the transcriptome changes of a primary microglia for the 3BP and the lonidamine and Iype treatments were assessed by RNA sequencing. To identify the biological functions by HK inhibition in microglia, we subject the significant DGs, different expression genes of these groups to GO analysis, gene ontology analysis of biological processes, and focus on the biology process commonly shared by these this three groups, we found that fatty acids and the lipid metabolism process was clustered and found to be reached in these groups. We also performed metabolomics and also found that it was there is a shift to lipid metabolism. We also used AI machine learning to find which metabolic pathway was enriched. Also found that top 10, there's 7 of top 10 pathway was enriched in lipid metabolism. Next, we also use carbon 13 flux metabolism to see the metabolic flux. We can see that also it was there's a metabolic flux to lipid metabolism. This result further confirmed the lipid metabolic is activated by HK inhibitor. Next, we measured the mRNA expressions of the key genes involved in lipid metabolism. Among of these genes, the MR levels of lipoprotein lipase (LPL) increased most dramatically in microglia treated with lonidamine and 3BP. Moreover, the LPL is also ranked the third change in metabolic DGs, different expression genes in the above RNA sequencing analysis. LPL is hydrolysis triglycerides in lipoprotein. Furthermore, we also analysis publicly available single cell microglia RNA-seq data and divided them into two groups: the high HK2 express groups and low HK MRI express the groups of microglia. We found that the genes related to lipid metabolism are increased in HK2 low MRI expression group, including the LPL. We can see this is the high HK express groups, and this is a low HK express groups. We can see this lipid metabolism increase in the low HK groups. Express of genes related to cellular homeostatic lysosomal function and DM stage 1 genes, stage 2 genes also increased in this single cell RNA sequence, reveal the close correlation between the conversion of energy metabolism and microglia's functions. By WB Western blotting, we found that both the pharmacology inhibition or gene deletion of HK2 lead to increase of protein and the MRI levels of LPL. And overexpression of HK2 decrease related to the decreased levels of LPL expression. You can also see that in the immunostaining, we can also see that after deletion of HK2, we can see that the LPL expression was increased. Then we use LPL inhibitor to treat. You can see that this LPL inhibitor abolish the promotion of ATP production and phagocytosis induced by HK2 inhibition in primary microglia. All this data indicate that ATP generation induced by HK2 inhibition is dependent on LPL in microglia. Finally, we explore the mechanism underlying the LPL expression regulated by HK inhibition. Lonidamine and 3BP inactivates HKs to inhibit the first step of the glucose metabolism, leading to a reduction of downstream glycolysis metabolites. We speculated that it is not the total glycolysis inhibition, but rather the change of a certain glucose metabolites that can regulate the microglia functions, especially the phagocytosis process, through increasing the ATP levels from lipid metabolism. To further test this gas microglia were treated with extra glucose 6-phosphate, fructose 6-phosphate, and FVP. In the presence of HK2 inhibitors, notably G6P and F6P, but not FVP, blocks phagocytosis, ATP and ATP production, and LPL expression, and in microglia, pre-treated with lonidamine or 3BP. Lucifer's reporting assay further confirmed that G6P and F6P, but not FBP, regulates the transcription of LPL in BB2 cells. Actually, the G6P and F6P regulates the ADPH and ANDP ratio through the pentose phosphate pathway, and the regulated G6P and F6P resulting from HK2 deficiency decreases the ADPH, which in turn stimulates the utilization of fatty acids. To test whether an ADPH regulates fatty acids utilization through LPL, we measured the ADPH levels in microglia treated with HK2 inhibitors and found that both lonidamine and 3BP significantly increased the production of the ADPH. ADPH supplementation blocks phagocytosis and ATP production, and and the ATP production. And reduce the transcription and expression of LPL expression in microglia. Furthermore, our study demonstrated that upon HK2 inhibition or deficiency, microglia sense the low levels of G6P, F6P, and NADPH, and thus mobilize lipid metabolism to produce ATP by stimulating the LPL expression. This compensating ATP production mechanism is unique in microglia and pivotal for microglia Iype clearance functions. So conclusion, we found that HK2 increased in microglia in plaque associated microglia in AD, in not only in AD model mice, but also in AD patients. And we found that HK2 inhibition, pharmacology inhibition or gene deletion increase ATP generation through lipid metabolism in microglia. Third, we found that the metabolic reconfiguration upon inhibition or deletion of HK2 in microglia is closely related to its function. Fourth, we found that HK2 we think that HK2 inhibition is potential AD therapeutic strategy. Okay, that's all. Thank you.
Okay, Wan Li, are you there, Wan Li? I guess not. Wan Li, no. Well, thank you very much, Dr. Ligue. Ben, do you want to comment, Ben? I guess Wan Li stepped away.
I'm sorry that I'm not talking about the disease in neurosurgery, although I was one neurosurgery medical student. I hope that will not disappoint you. I don't know whether you have interest in the research in Alzheimer's disease.
Well, we've all been through medical school and research, you know, so it's a relevant topic to everybody. So.
Yeah. Thank you, Dr. Lanli Ge. And I think it's a very nice presentation, and but it's a little bit complicated to understand, you know. Can you describe it in a very simplified sentence that what's the meaning for this research?
Okay. Actually, we usually found that there's glucose metabolism impairment in AD. But microglia, we found that microglia, this actually is microphage cells in brain. This kind of cell, microglia, has a very unique metabolism pattern. When we inhibit the HK2, actually is the first step of the glucose metabolism. Actually is when we inhibit this HK2, actually we think that when we inhibit this HK2, the glucose metabolism will decrease, the ATP will decrease, but actually the ATP is not decreased, actually is increased because through LPL, the lipid metabolism in microglia was activated. So through some metabolism sensing. So actually, in short, we found a unique microglia metabolic pattern that microglia can flexible to use different kind of energy, including glucose, including lipids. When we inhibit the glucose, actually increase the ATP production because the microglia can use lipid to produce more ATP. Actually, that was our finding in this research.
Okay, so making the more ADP is have a positive or negative effect.
Positive,
disease.
in fact, more ATP can give the microglia enough energy to do its function, like phagocytosis and migration to the plaque, to the plaque and phagocytosis of the plaque. Actually, is good for the to rescue the AD pathology.
Okay, thank you.
Thank you very much.
And thank you for giving me this opportunity to give you a presentation.
Yeah, okay, very good. Stephanie, do you have a word to say to Dr. Ligue?
Yeah, thank you, doctor. I was really amazed by your presentation because it's always interesting to learn even more about this kind of disease. And I think that your work is very thorough. So congratulations for that. And thank you, doctor. It was a really nice presentation.
Thank you.
Yeah, thank you. And I'm sorry to say, Iype is still in surgery, and as Dr. Ben will tell you, the job comes first, and then if you have time to come. So I guess we'll have to wrap it up, Dr. Ben. And
Where is
yeah,
Dr.
I haven't heard from Iype, so I think he's still in surgery.
Okay.
He had an emergency. I just checked with him, and hey, let me check, like one last check to see. So he hasn't. No, he hasn't answered back.
Okay. So Dr.
Ilian?
Erini,
Wanli, you there? Do you want to say goodbye?
Dr. Bennett, Dr. Eliane wrote on the chat saying that it's here instead of Dr. Iype.
Okay, I'm here. Yeah, I heard about it. So maybe we can invite Iype next time for the webinar, right?
Well, you know, we have Dr. Teo has agreed to present on the 18th. Well, perhaps we can, whatever you guys want to do.
okay, I think we have Elaine Dos Santos. He said I'm here instead of him.
Oh, okay. Okay, let's try here.
Mhm.
Estofos. Let me try to find him.
It's on the panelist section already.
Yes, it's already in the panelist.
Oh, he's in the panel. Okay, okay.
Mhm.
Okay, could Iype's replacement please introduce themselves?
Yeah.
Yeah. Okay.
So Santos Rubio will give
Hi.
the talk, right?
I'm sorry. Do you hear me?
Yes.
Yeah, yeah.
Okay. Okay. Very excellent.
I'm sorry.
Okay.
Hi. I'm
No
not
problem.
sure if it's I'm not sure if it's my cue to talk, but I understood yesterday that Mikael he asked me to be here. Is that true?
No, I'm sorry. No, we're talking to Miguel about starting a Portuguese channel in neurosurgery
Yes.
in
Exactly.
Africa. So
I know.
That's
I'm
okay.
one of the founders.
We'll talk later. It's kind of a private thing. Okay.
Okay.
So
Good. I'm
that's the
out then.
presentation. We'll talk to you later. Okay.
Okay. Good.
Okay. Very good.
Thanks.
Okay, Ben. Dr. Mario Teo is scheduled in 2 weeks. So I guess we'll see you then, correct?
Yeah.
Okay. Okay, Stephanie, thanks a lot. Thanks, Ben. Thanks, Wanli. And we'll see you in 2 weeks.
Thank you,
Thanks,
Dr.
Dr.
Bennett.
Ligue.
Mm.
Thank you.
Thank you,
Thank
Dr.
you.
Okay.
Lee.